There's a special class of boundary value problems called eigenvalue problems, and they're ODE eigenvalue problems, and we're going to look at them over the next few videos. First of all, let's have a quick look at, go back and refresh our memory as to matrix eigenvalue problems, and these arise in linear algebra in a whole range of different guises. So in linear algebra, any square matrix A has scalar eigenvalues lambda, and by scalar I just mean their numbers. The eigenvalues of a matrix A are determined from solutions of the equation AX is equal to lambda x, where x is an unknown vector. Although x is equal to 0 is a trivial solution for all lambda, there are special values of lambda where the equation is satisfied for non-zero x, and those are the things that we're usually interested in. These special lambdas are called eigenvalues. And the non-zero vectors x that correspond to each of these lambda are called eigenvectors. And an n by n matrix has n eigenvalues. They don't have to be unique. Some of the values can be repeated. It just depends on the matrix. So, with that in the back of our minds, let's have a look at a canonical ODE eigenvalue problem. So we're going to look at the problem of a vibrating string. This is typically what the mode shape looks like for a vibrating string. Usually the string is clamped at each of the endpoints. There are some nodes where the amplitude of the string is 0 and the string oscillates between a negative and positive fraction, and this usually looks like a sinusoid. The partial differential equation for the string displacement, d of x and t, is given by the wave equation, and that's written as the partial derivative d squared d dt squared is equal to c squared partial derivative d squared d dx squared. If we use separation of variables, in other words, we write our solution d of xt as equal to theta of t times y of x. We substitute that into the PDE and we divide things through. We end up with an expression 1 on theta d squared theta dt squared is equal to c squared 1 on y d squared y dx squared. The left-hand side is only a function of time and the right-hand side is only a function of x. And because we can't have a function of time equal to a function of x, they both must be equal to constants. And we're going to call that constant minus lambda squared, and that will become apparent as to why we're using this nomenclature a little bit later. Or we can write d squared y dx squared is equal to negative lambda squared y, and that's an equation that looks like an equation that's more familiar. So y of x here represents the spatial mode shape. It doesn't say anything about how this string is operating or vibrating in time. That comes with the theta solution that we're not going to consider here. Now we need boundary conditions for the displacement. So we're going to assume that the string has a length of L, and we're going to say it's clamped at both ends so that y of 0 is equal to 0 and y of L is equal to 0. So that represents that point on the left-hand side and that point on the right-hand side. So if lambda squared is equal to 0, then the only solution is trivial, and that is that y of x is equal to 0. That's a pretty boring solution. So the equation only has a non-trivial solution if lambda squared is non-zero. Worth also mentioning is that the eigenvalues lambda squared must be positive for physically meaningful solutions. And that comes from the physics of the situation, and we're not going to go into that here.